Welcome to the world of material science. My name is Professor Bonnet. In this video, we won't yet be talking much about materials. Instead, we will be looking at the atomic structure and the different types of atomic bonds. But first, let's begin with a classification of materials. We distinguish between three general categories: metals, nonmetals, and natural substances. Natural substances can be divided into mineral natural substances and organic natural substances. Materials such as wood, but also concrete, are natural substances. Nonmetals can be divided into semiconductors, nonmetal inorganic materials, and nonmetal organic materials. Ceramics, for example, are nonmetal inorganic materials. Plastics, such as polyethylene, polypropylene, or polyvinyl chloride, are nonmetal organic materials. Within the category of metallic materials, the focus is on steel and ferrous materials. All other materials are known as non-ferrous metals. This includes, for example, copper, tin, aluminum, and nickel. After working through the following videos, you will also know what it meant by designations such as S235 or X5 CRNI 1810. To understand the structure and resulting properties of the various classes of materials, we need to get to know the different types of bonds. The different types of bonds are a result of the structure of atoms. Atoms consist of elementary particles: electrons, which have a negative electric charge, protons, which have a positive electric charge, and neutrons, which have no electric charge. Each atom has the same number of electrons and protons, so that as a whole the atom is electrically neutral. The figure shows a carbon atom according to Bohr's atomic model, which states that electrons move on stable orbits around the atomic nucleus. The nucleus, which consists of 6 protons and 6 neutrons, is orbited by 6 electrons. 2 revolve in the inner shell and 4 in the outermost shell. However, the proportions shown here are not realistic. The nucleus of all known atoms is just 1 out of 10,000 to 1 out of 100,000 the size of the atom's radius. If the nucleus was 1 centimeter, which is approximately the size of a cherry stone, the diameter of the whole atom would correspond to the height of the Cologne Cathedral, which is the world's 3rd tallest church building. All atoms that have the same number of electrons in neutral state belong to one chemical element. There are more than 100 different chemical elements, which means elements with more or less electrons and protons. The individual electrons of an atom can be located at different distances from the nucleus and can also vary in their energy state. The electrons are in certain energy levels, which are also called shells according to Niels Bohr's atomic model. Electrons in the outermost shell are called valence electrons. They play a decisive role in the chemistry and thus in the types of bonding as well. The electron configuration can be found in the periodic table of elements. The main group's number corresponds to the number of valence electrons. The period corresponds to the number of shells. Noble gases, which are marked in white in this periodic table, are inert. They are chemically stable because they don't need additional electrons. They have a full valence shell, which means that they have 8 electrons in their outermost shell. Helium is one exception, since there is only room for a maximum of 2 electrons in the innermost and smallest shell. All atoms strive to achieve this state in their valence shell. We call this state the noble gas configuration. Except, of course, in the case of noble gases themselves, electrons are either lost or gained to achieve the stable noble gas configuration. Atoms with few valence electrons strive to lose them. These atoms are called metal atoms. Atoms with many valence electrons strive to fill the valence shell. These atoms are called nonmetal atoms. The fewer electrons there are in the valence shell, and the further away the shell is from the nucleus, the stronger is the atoms strive to lose electrons. Thus, their metal character increases. The more electrons there are in the valence shell, and the closer the shell is to the nucleus, the stronger the atoms strive to gain electrons. Thus, their nonmetal character increases. This is how an electrically neutral atom becomes a positive ion in the case of metals or a negative ion in the case of nonmetals. Due to their charge, these ions exert a force effect on their surroundings. As an example, let's have a look at cesium. Cesium is a chemical element with a symbol Cs and atomic number 55. In the periodic table, it is located in the main group 1 and the period 6. The numbers show that it has only one electron in its valence shell, which is very far away from the nucleus. Thus, cesium is not only a metal, but an extremely reactive metal. It reacts spontaneously and violently with air, which is why it is stored beneath inert gas in glass ampoules. Let's now move on to types of bonding. Chemical bonds are the basis for the formation of molecules and crystals, and therefore one of the most important fundamentals of the chemistry of materials. The question is, which combination of metal and/or non-metal atoms leads to which type of bonding? If a non-metal atom reacts with another non-metal atom, both atoms strive to gain additional electrons in the valence shell. This can be achieved by electron pair sharing, which we call the covalent or atomic bond. Hydrogen gas, for example, does not exist of individual hydrogen atoms. But of molecules consisting of two bound hydrogen atoms. Due to this electron sharing, both hydrogen atoms achieve the state of a noble gas. This means that both hydrogen atoms now have two electrons, making their valence shell full, like in the case of the noble gas helium. One could think that the positively charged nuclei repel one another, but the negatively charged electrons keep them together. They form an electron pair. Thus, covalent bonds result in molecules. If the valence shell lacks two electrons, like in the case of oxygen, two covalent bonds can be formed. We call this a double bond. Further examples of common molecules are methane, CH4, ammonia, NH3, and hydrogen sulfide, H2S. Furthermore, there are so-called macromolecules, which consist of more than 10,000 single atoms. Examples are deoxyribonucleic acid, DNA, or the material category of polymers. What is of interest for us concerning material science are the properties resulting from the different types of bond. At this point, we can note the following about covalent bonds. Substances consisting of small molecules formed by covalent bonding are gaseous or liquid at room temperature. Examples are methane, ammonia, water, or alcohol. Substances consisting of large molecules formed by covalent bonding, for example polymers, are solid at room temperature. Crystals are substances with a clear periodicity in all three dimensions in space. Their atoms are bonded by covalent bonding, making the crystal extremely hard. The best known example is diamond. A diamond is a crystal lattice of carbon atoms in covalent bonds. What happens then if a nonmetal atom meets a metal atom? One of them is obviously happy to lose its electrons, while the other one is happy to gain it. In this case, one or more electrons can be transferred from one atom to another atom, resulting in positively and negatively charged particles, the so-called ions. The resulting type of bond is called an ionic bond. This type of bond is present in the majority of nonmetallic inorganic substances. Table salt is chemically sodium chloride. The chlorine atom gains an electron from the sodium atom, thus creating a NaCl molecule. In a solid body, the electrostatic forces cause a positively charged cation to be followed by a negatively charged anion. If an external force acts on the ion lattice, the shift of a part of the ions by one interatomic distance would result in a juxtaposition of only cations or only anions. Due to the like charge, the resulting repulsive force would destroy the crystal. Thus, plastic deformability is not be expected with ion bonding. The last possible combination is a reaction of a metal atom with a metal atom. As we've already seen, metal atoms generally strive to lose electrons to achieve the noble gas configuration. Therefore, they form positively charged ions. If metal atoms react with metal atoms, there are no atoms that can gain electrons. As a result, the lost electrons are left unbound. These free valence electrons form an electron gas. Thus, we can say that a metallic bond is characterized by positive charged atomic cores which interact with an electron gas. The good electrical and thermal conductivity of metals is due to the fact that the valence electrons in metals are not fixed in any one position. In contrast to the ion lattice, a change of position of individual atomic cores in a metal lattice does not change the charge distribution between the atomic bodies and the electron gas. Therefore, the atoms can be shifted against each other without destroying the lattice. This explains the good to very good plastic deformation of metallic materials. Thanks for watching. If you're new here, consider hitting the subscribe button. There will be regularly new videos on material science you might be interested in.